Today we're going to look at an AP Physics C problem from the 2025 exam. We're going to look at the first problem, which is based on Newtonian physics, and let's jump right into it. So here is the problem. Two blocks, 1 and 2, slide toward each other on a horizontal surface. Block 1 has a mass m and slides in the direction of positive x with a constant speed 2v naught. Block 2 has a mass of 6m and slides in the negative x direction with a constant speed of v naught, as shown in figure 1. The blocks then collide and stick together. So we're looking at a perfectly inelastic collision. They slide and stick together. Another way of thinking of an inelastic collision is we're going to make as much heat as possible. The collision occurs from the time t0 to t of the collision, right? So t sub c, they're recognizing as the time of the end of the collision. So clearly this is headed into an impulse problem because we're talking about the time of collision. After the collision, where t is greater than the impact time, the blocks move together with the same constant speed. Well, I already said that because it said the blocks stick together. So they move together with the same speed is the same thing as them sticking together. The diagram in figure 2, if we come down to here, this is figure 2. And what's happening here is it's saying, block 1 has a particular momentum before the collision. And so the momentum before the collision of block 1 is just going to be mass times velocity, or 2mv naught. And so it kind of gives you scale here. So this goes in the positive 2 blocks direction. So this arrow is going to represent 2mv naught. And so now we're going to be asked to determine the momentum of block 2 before the collision. And the momentum of block 2 is going to be in the negative x direction. And again, it's going to be the mass times velocity. So 6m v naught. And so if we were to draw this arrow here, it would go in the minus x direction. 1, 2, 3, 4, 5, 6. And so it'd be a vector arrow pointed in the minus direction to the end of the 6th block. And the momentum before collision of the 2 block system is going to be the sum of those 2 arrows. Clearly, the momentum of the 2 block system is going to be the sum of the momentum of block 1 and the momentum of block 2. Remembering that momentum is a vector. This is just tip to tail. Another way of thinking that is to go 2 blocks to the right and then 6 blocks to the left to make a total of 4 blocks to the left. And then it's going to ask the momentum after the collision, which is clearly the same as the momentum before the collision, because in any collision, momentum is conserved. And so that would be the answer to A. We can draw that out briefly by looking at the document camera and coming over here. So we have a block of mass m going in the positive direction with velocity of 2v0, and we have a block of 6m going in the negative direction with a velocity of v0. The momentum of block 1, if we're going to say that it's 2 blocks in the positive direction, so this would be 2mv naught, then block 2 is going to have a vector in the negative direction of negative 6mv naught. If we add these together, we get a vector of minus 4mv naught, and this is all before collision. And so if we're going to look after, we recognize that it's going to be the same as before. The momentum is conserved. So whatever the momentum of the system is before the collision is going to be the momentum after. The momentum of block 1 is clearly going to change before and after the collision. And the momentum of block 2 is going to change before and after the collision. And the change in their momentums will be equal and opposite because total momentum is conserved, but the total momentum of the system will be constant before and after the collision. So over here we would have the same as the total momentum after collision is minus 4 mv naught. So if we look at the second half of this problem, during the time interval of the collision, this is just the time of the collision, a force F is exerted on block 2 by block 1 along the x direction as a function of time that is modeled by the sine function. So the force as a function of time is going to be some F max sine of some constant times t, where a is a positive constant, F max is the magnitude of the maximum force exerted on block 2 by block 1 during the collision. Of course, the only thing that would change if we said the force exhibited by block 2 on block 1 or by block 1 on block 2 is just the sign of the force being exerted. It could be positive or negative. And we do have to be careful about these things when they get to a final answer. But ultimately, I don't pay attention to the sign one way or another until something is being added or subtracted or we get to a final answer. I find that trying to track the sign exactly can actually lead to sign errors when common sense is a better indicator of whether we should add or subtract. So the question is, derive an expression for F max. Express your answer in terms of m, v naught, a, t sub c, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. I think the most important thing to do is to start off by figuring out what is even being asked. It gives us this equation that the force as a function of time is equal to F max sine of a t, where a is a constant. We can solve for what a equals right off if we just recognize some common sense situation that this is a sine function that's going from t equals 0, t0, to some time of collision, tc. And what we know is that before the blocks collide, there's no force. And as soon as they collide, the force begins. So we know that this is the start of the collision and that the force at the start of the collision is 0. And we know that as they collide, the force increases, reaches a maximum, the blocks start to separate, and the force falls off. And eventually, no force is going to be applied to the blocks, and that's going to be the end of the collision. So we have conceptually our zeros applied. And so we can say that the sine of AT at the end of the collision is equal to 0. And hopefully then you can see, and of course it's only half a period in. So hopefully just conceptually you can see that A is going to equal pi over TC. And this is going to be essential to our solution when we try to get a solution for an expression for F max. And of course, we got to remember our fundamental principles where we're coming from. The change in momentum on one of the blocks, let's just say block 2. We could say block 1, it doesn't matter because the change in momentum for block 1 is the same as the change in momentum for block 2. But the change in momentum is going to be equal to the integral from the start of the collision to the end of the collision of force as a function of time for the interval of the collision, dt. And so a few things have to happen here, but first, maybe we should just start here. We're going to need a value for the change in momentum of block 2. The momentum of block 2 to start is minus 6 mv naught. The momentum total of the system, remember, is going to be minus 4 mv naught. And so what we have to do is solve for the velocity of the two block system after the collision. And so we know that the total momentum before and after is the same. The total momentum we solved for minus 4 mv naught, which is going to equal 7 mvf. Because the total mass of the two block system is 7m. And so whatever that mass is times the final velocity will be the momentum of the system. So now we have a relationship between V naught and V final. And in fact, we can do some really simple math and say that V final equals 4/7 of V naught. And, you know, we could start tracking signs and such, but I think what's more important is just to look at the system itself and say V naught is in the positive direction. Clearly, the momentum of the system is in the negative direction. So V final has to be negative. And just conceptually, I think we can slow down for a second and say this needs a negative sign in front of the 4/7 V naught. Of course, 4/7 is a little bigger than half. The final momentum will be going to the left, and the final velocity going to the left will be more than half of V naught. Remember, V naught is the velocity of block 2 at the start. Clearly, the system's going to be moving to the left after the collision. And so the velocity after the collision is going to be less than V naught. And it's going to be more than half of V naught because it's the big block hitting the little block. And we can just conceptually make sense of that to make sure that our system is reasonably defined. And I believe that it is. So we end up with a final velocity of this two block system of minus 4/7 V naught. What we want is the change in momentum for block 2. So the initial momentum of block 2 was equal to minus 6 mv naught. And the final momentum of block 2 is equal to 6m times minus 4/7 V naught, which is equal to minus 24/7 mv naught. And so then we can get the change in momentum for block 2 is equal to the final minus initial, minus 24/7 mv naught minus a negative 6 mv naught. And of course, we should be able to make conceptual sense of this. If we have one block, heavy block, running into another block, we said the final velocity of the two block system is going to be going to the left at 4/7 V naught. So the change in momentum should be in the positive direction because it starts with a momentum in the negative direction and ends with less momentum in the negative direction. So the change in momentum should be in the positive direction. So when we end up with this, we should end up with a positive number. And if we start doing this math, we realize real quickly we're in safe waters here. -7 plus 42 over 7 all times mv naught, which equals what? Positive 18 over 7 mv naught. And that's our change in momentum for block 2. So the change in momentum is equal to 18/7 mv naught. And this is what we were looking for, the change in momentum of block 2, because the change in momentum of block 2 is the impulse, and the impulse is the integral of force as a function of time times the change in time. And we're integrating this from 0 to the total time of collision. And so now we have everything we need to solve this integral for F max. Remember, this is the integral from 0 to TC of now F max sine of pi over TC T dt. We can evaluate this integral by, well, I mean, probably the easiest way to do it is just do a u substitution, let u equal pi t over tc. And so then du equals pi over the time of collision dt. And then, of course, dt equals the time of collision over pi du. And so then I can say this whole integral equals t time of collision over pi times the integral from 0 to pi, recognizing that at the time tc, t over tc, tc over tc will cancel, and u equals pi. F max sine of u du. And of course, the integral from 0 to pi of sine of u du is 2. I don't know if you need to see that because the integral of sine is cosine. The cosine of 0 is 1. The cosine of pi is -1. 1 minus -1 is 2. Hopefully that's familiar to you at this point. But I'm just going to move on from there. The time, 2 times the kind of collision over pi f max equals the change in momentum of block 2, which above we said was 18 over 7 mv naught. And so now we can come up with an expression for F max, which is going to equal, well, this 2 will come over, reduce with that 18 to make 9. So let's just let that be 9 pi over 9 pi mv naught over 7 times the time of the collision. And that would be our answer for F max. So what we have again is this 2-block system, and it's saying block 1 of mass m, block 2 of mass 6m, and it's saying that this has some velocity v1, where this starts with an initial velocity of v0. And then it's saying after the collision, block 2 also has a velocity of v0. So the momentum of block 2 did not change. This is a weird question because there's no way for these actually to collide and for the momentum to not change. The only hypothetical situation where that could happen is if these blocks collided and the initial velocity of the block 1 was also v0 to the left. That can't happen because they would never collide if they have the same velocity in the same direction. So I don't know what they're looking for here. It's kind of like a trick question. Somehow say that they never could collide because the only way they could collide is if V1 is equal to V0. And so that is the first problem on the 2025 APC test. Hopefully that's helpful. Thank you.